Okay, so our speaker now is Patrizia Vignolo from Institut de Physique de Nice, and she will talk about symmetry oscillations in strongly interacting one-dimensional mixtures. Please, Patrizia, the floor is yours.
Thank you very much, Gregory, for this introduction. Thank you to all the organizers for having invited me. It's an honor to be here at ICTS and to be able to have the opportunity to present you this result of this work on symmetry oscillation and strongly interacting one-dimensional mixture that I have done in collaboration with Anna Minguzzi, Mattias Albert, Silvia Musolino, and also Giovanni Pecci and Gianni Opetidiallo. So the system I have in mind is a mixture that can be done with ultra cold gases in one dimension. And to arrive to tell all my story, what I need is to remind you what happened in one dimension when do you have strongly interacting bosons and how is the mapping with a system of spinless fermions. So this is something that happened in 1D. Boson fermions behaves a little bit in the same way. And this helped to build an exact solution for a strongly interacting trapped mixture. And when you have an exact solution, you really can understand the physics and you can understand the relation between the spectrum, the symmetries, and also the contact that is a quantity that I will define later for a mixture where there is permutation symmetry. And it's also possible to understand when you break this symmetry on the property, for instance, on the ground state. And thanks to this mapping, we are able to have an exact solution, almost exact solution for the dynamics. And so thanks to this, I will arrive to my story about the symmetry oscillation. So let's start. So what happened in a one-dimensional world? The system, so let's start from a single component boson gas that is described for this many-body Hamiltonian, in which there is the kinetic term, a contact interaction term, and eventually a potential, an external potential. This model without the external potential is the Liebig-Lininger model that is integrable, indeed when the potential is flat, but is not integral for any type of potential or for a generic interaction strength, but become again integrable in the limit of very strong interactions for any potential. And this is the limit in which I am interested, when the interaction strength is very, very large and is repulsive. So what happened in this is the Tonks-Girardot limit, and what happens in this limit from the point of view of a many-body wave function. Here, if you take the many-body wave function for two particles, if there are no interactions, the two particle bosons, then they both occupy the lowest, here I'm zero temperature, the lowest energy orbital. But when you start to input the interaction, there is a cusp that appears, and when the interaction goes to infinity, this cusp touches the zero here. So what happened? It happened that if I have two bosons in a line world, they cannot be at the same place at the same time in their world. So this is very similar to a Pauli principle. Interactions for bosons play the role of Pauli principle for non-interacting fermions. So thanks to this, we are able to write the many-body wave function for a strongly interacting system for the bosons here, going through the many-body wave function for non-interacting fermion, just making a symmetrization operation. So what is the consequence? That all observable that does not depend on this symmetrization operation are the same, such as the spatial density, the density-density correlation function, the dynamical structure factor. So how do you proceed in practice? So let's take, for instance, just two bosons, two strongly Tonks-Girardot bosons that you put in harmonic potential. You start building the many-body wave function for fermions, for spinless fermions, and this is a very textbook exercise. You build your Slater determinant using this single particle orbital for the harmonic potential. And so this, you calculate your many-body wave function for the two fermions that is antisymmetric for the exchange of the two particles. Now, what means that you how you get the many-body wave function for the Tonks-Girardot bosons, you symmetrize. And here the symmetrization is very simple. I have just to put this absolute value here. But what I'm doing conceptually, what I'm doing is this. I'm considering all the in the particle space, all the possible sector in which I'm ordering the particle. Here I'm considering just particle, the sector in which I put the particle 1 on the left and the particle 2 on the right, and I'm saying, okay, the many-body wave function here is the many-body wave function for fermions, and then in the sector in which I put the particle 2 on the left, particle 1 on the right, is minus the many-body wave function for the fermions. And if I have n particles, I have to consider n factorial sector, and for each ordering of the particles, I have to adjust the sign of many-body wave function to adjust the symmetry. So what is the effect of this symmetrization operation? Okay, it doesn't enter in the density profile, but it enters in the momentum distribution, for instance. It is something that can be measured easily in ultra-cold gases. In the experiment, you release your gas and you can measure the velocity distribution. So you have access very easily, let's say, to this quantity. So for fermions, silence fermions, if you have here in a harmonic potential trap, you have a sort of potato shape, is not tall and is large. And for Tonks-Girardot bosons, the effect of this modulus around x2 minus 1 have two effects. You have a peak momentum distribution, and this is an effect of the presence of a quasi-condensate in our system. And also there are very large tails. There is the momentum distribution decay with p minus 4, this algebraic law, with a coefficient in front here, c, that is called the time contact. And there's a quantity that I like a lot, and take an account really about the symmetry of the system. So let me tell you about something more about this quantity, the contact. Is something that is not only in the Tonks-Girardot gas, but also for any strength of interaction. What is important are contact interaction. Is not only in 1D, but also in 2D or 3D. And there were some very nice experiments of Debbie Jean in strong interacting Fermi gas in 3D, and a nice experiment by David Clement in condensate bosonic gas. And also what is important is it does not appear only the tails of momentum-based distribution, but is connected to some bulk properties of a gas. Indeed, is proportional to the product of interaction strength and the interaction energy, namely to minus the derivative of the total energy with respect to the inverse of the interaction strength. But you have to be careful. So you could think that the contact is proportional to the interaction energy, but you have to be careful, because if you are in this limit of interaction that go to infinitive, the interaction energy is 0, and the interaction strength is infinitive. What is different from 0 is the product between the interaction strength and interaction energy. So what is the contact in this limit? If you make the calculation, and you develop your calculation, what you obtain, you can do it explicitly using the cusp condition that connect the value of the many-body wave function when you try to put two particles on the same point times the interaction strength. This is connected to the discontinuity of the derivative around this point. So what is the contact? The contact counts all the cusps in the many-body wave function, so all the symmetric change in the many-body wave function, and is proportional to the slope of the cusp, so how the particle brush against. So it's really something that is induced by interaction, but taking account of the symmetry of the many-body wave function. And this will be useful for later. So now what happens if I have a mixture? So what is a mixture? You can have this atomic gas in a different spin state. They can be bosonic or fermionic. So what I have in mind are, for instance, bosonic mixtures. So here represented by different pink color, the pink type, different type of pink, that have very strong interaction intra-species. but also we can consider the other mixture that I have in mind are fermionic one, in which, of course, there is Pauli principle between fermions of the same species, so there is not a wave interaction term, but you can have very strong repulsive interaction between fermions belonging to different species. Both these two systems can be mapped again on a gas of spinless fermions. Why? Because the many-body wave function for spinless fermions has the good node for also these two cases, because here the nodes are induced by the interactions, here they are induced or by the interaction or because of the Pauli principle, and then this solution as the spinless solution, spinless fermion solution has very good rules for exchanges fermions that belong to the same species. They give, if I adjust the symmetrization, they give the good rules for exchanges bosons that belong to the same species. What is missing the interspecies exchange rule. And this is the basis of a large ground state degeneracy in the limit of very strong interaction this degeneracy is given by variation between all the particle permutations, that is n factorial, divided all the permutation in each species. So how can I use the spinless fermion solution to build the solution for the mixers? It's very simple. I will do exactly how you proceed for the Thomson-Girardot gas. I separate my particle space in sector. This theta function take account about this. This P is a permutation operator, so I take all the possible order of the particles, and I'm saying in each sector, my many-body wave function is proportional to the spinless fermionic one times a factor. This factor, if I have a single particle, a single component bosons, is just plus and minus 1. Now I don't know. And how I can evaluate these terms IP, I can do an expansion of energy in 1 over G, because the question is that the limit of G infinite is a limit, but usually you have G that is large but finite, so we look for the energy in 1 over G. So when you have to minimize this term that is the derivative of the energy with respect to the inverse of interaction strength, I recognize here that this is minus the contact, except some H bar and mass. So what I'm saying that when the coefficients P that minimize the energy, maximize the contact, namely they maximize the symmetry of the many-body wave functions, because the contact take into account about all the symmetric exchange. So more in details, if you want all the P for all the state of a manifold.
Sorry, just one question. So,
yes.
Sorry, the contact was called C, right? So what is
yes,
K? So K is
because the different are really some H bar and mass. One is something that is a question of the dimensionality, but it's just this. I'm sorry. So it's because once is as the dimension of a momentum distribution times P4, and this is energy times G. So it's a question of dimension, sorry. But it's exactly the same except some H bar and mass term. So thanks for the question. So more in detail, if I want all the state of my manifold that of the energies that are degenerate in infinite G, but are not degenerate when G is large but finite, what I'm doing is an expansion of on the Hamiltonian, projecting using as basis to project it the basis of the spin configuration that are less than the all possible set. We call it the snippet basis, but this is just technical. And if I do this and I diagonalize this, I obtain all of my P. But okay, this is I have no time to tell this, but if you want, you can ask me later. This effective Hamiltonian that I obtain doing this operation is can be mapped on a spin chain Hamiltonian. So so I have my effective Hamiltonian, I can calculate my eigenstate, And there is no surprise if the symmetry is well defined in my initial model, each eigenstate has a well-defined symmetry. So what this means and how I check the symmetry of my state. We use some operators in which we consider the cyclic permutation of K element. Why? Because the eigenvalues of this operator have a correspondence with a tableau, Young tableau. I don't know if you are familiar with the Young tableau, but the idea is very simple. You have a number of boxes equal to the number of particles. If the boxes are horizontal, there are symmetric exchange. If they are vertical, there are antisymmetric exchange. So this corresponds to a many-body wave function of 5 particles that is fully symmetric. This is fully antisymmetric. And these are more exotic symmetry in which we have some particles that have symmetric exchange and antisymmetric exchange. Nevertheless, so what we do, you use if you have a small number of particles, the gamma 2 is good enough to label your state, and the gamma 2 is the sum of all possible permutations. So let's say that this is our main symmetry witness, and we are able, once we have a many-body wave function, to check at which Young tableau belongs this solution. So we are able to check the symmetry. So you can do the exercise, you can take 2 plus 2 SU2 fermions or 2 plus 2 SU2 bosons, and then you can calculate the state and the spectrum, and it's function of 1 over G. All the states are degenerate when G is infinitive, but then there is the energy is, you see that the energy is lower when the state is more symmetric. If you have 2 fermions, the way to have a more symmetric wave function is to put the 2 fermions like this for the point of view of the Young tableau. So you have this square symmetry. If you have 2 plus 2 bosons, the most symmetric is this, and you have this one is a fully symmetric state. And here, what the slope of the energy here is equal to the contact, and this is the relation between C and K. There are also H bar. So the story is that the eigenstate have a given symmetry, that this come out, of course, in the energy, but also in the contact. And if I look the momentum distribution of, for instance, here for 2 plus 2 SU2 bosons, there is not only the tails that depend on the symmetry, but as I told for boson and fermions, also the peak of momentum distribution. More the state is symmetric, the most is high the peak of momentum distribution. So now what happens if I break the symmetry? The way to break the symmetry is, for instance, for boson to take two different intra-species interaction strength and interspecies interaction strength. So if two are equal, this interaction strength, I have a SU2 situation that from the point of view, my effective Hamiltonian, where the interaction is large, can be mapped on the XXX spin chain Hamiltonian. And when I break the symmetry, that I put a different interspecies interaction strength, my effective Hamiltonian, this is for spin chain guys, it can be mapped on XXZ Hamiltonian. So what is the result is that, of course, if I have the permutation particle is conserved, I have 2 plus 2 bosons. The ground state has to be the most symmetric possible, so is the line, the good Young tableau that represents this state. But when I break the symmetry, the ground state is not a well-defined symmetry. I found a mix of symmetries. And what is the effect on the contact? That, of course, the contact for the state in which I break the symmetry is lower because I have less symmetric exchange in my many-body wave function. It's a small deviation of, this is the ratio between the two contacts. This deviation is small because I'm breaking just a little the symmetry. And in the peak of momentum distribution, this effect become very large, that I'm losing coherence when I break the symmetry, when I increase the number of particles. The thermodynamic limit, the peak is, for the symmetry breaking case, is 1/2 of SU2. So let's say that also when you break the symmetry, you have an effect in the contact and the peak moment distribution. So now what happens when I go to the dynamics? So let me do some more publicity to this method of fermionization. Thanks to this fermionization, we are able also to study the dynamics. And this is not trivial for quantum systems. So we are very proud of this. And so in general, what you have when you put the time dependence here, you should have a time dependent in these AP coefficients that give the spin population of each sector, but also a time dependent here in the many body wave function for the spinless fermion on which I'm mapping the system. But I can think to experiment in which I don't touch the total density, and so I don't, I excite only the spin. If I do this to solve this, the dynamics of the system is really more simple because the effective Hamiltonian that I obtain does not depend on time, is or the X Hamiltonian or the XZ Hamiltonian. So it becomes very simple and you can study the dynamics. So what do we expect? We expect that if the Hamiltonian preserve the particle exchange symmetry, there is a symmetry conservation. If a state, I start with a state that is a given symmetry, I expect that the symmetry does not evolve. But if my Hamiltonian breaks the symmetry, I'm expecting that the symmetry is not conserved, of course. So particle state of a given permutation symmetry are not diagonal, the basis of my Hamiltonian. So I'm expecting that the symmetry is not conserved, that I go from, let's say, a fermionic to a bosonic state during the symmetry, during the dynamics. So what reminds us this? This is remind about neutrino oscillation. Indeed, this is what happened for the neutrino physics. Neutrino state of a given flower are not diagonal the basis of their dynamical evolution. So during time evolution, the neutrinos evolve from one flower to another. But for neutrino, I can check if I are leptonic. Okay, I'm not expert in neutrino, but there is a way to check the flavor of a neutrino. For symmetry, I cannot just observe a Young tableau dancing. So how can see this symmetry oscillation? Is all the talk that I'm preparing, what I go to say. I can look, of course, to the momentum distribution, because, as I told you before, the momentum distribution, the peak and the tail momentum distribution are higher when the symmetry is larger. And so what is the experiment that you have thought? Is an experiment in which, for instance, the experimentalist can prepare a state in which is not the ground state from the spin point of view, in which you separate the spin up and the spin down in your trap, so you have a wall domain. In real space, there are spinor oscillation. There is a lot of fantastic physics to study, but it's not the object of this talk today. So the question is what happened in the momentum distribution? And that happened this. If the system evolves with SU2 Hamiltonian, the momentum distribution in practice does not evolve in time, while when you break the symmetry, you have a large oscillation of the momentum distribution. And to be more quantitatively, here you have what we have plot here is the effective, the aspect, the expectation value of my witness, symmetry witness operator, this gamma 2 here. The blue curve is for SU2 case. It doesn't move, the symmetry doesn't evolve. And the orange case, orange curve is for the symmetry breaking case. And here below, you have we have plot the peak of a momentum distribution for the SU2 case and the symmetry breaking case, and the contact for the SU2 case and the symmetry breaking case. And you observe that you have the same oscillation. So really, the momentum, the peak And the momento distribution and the Gautam distribution follow the symmetry of the system during its evolution. So, conclusion, I've shown you that in a line world, you can map a system of strongly interacting boson on spinless fermions. This allows to solve exactly this system. This is known for a long time from Tonks and Girardot, but this allows this fermionization also to solve exactly a mixture of bosons or fermions when you have different species of bosons, different species of fermions. So this allows really to have access to the many body wave functions, so to understand everything of your system. And so we have understood the connection between the symmetry and the different state. And there is a strong signature of a symmetry in the momentum distribution that come out. And that the fermionization allows also to solve exactly in 1 over G. Our model is exactly 1 over G for the dynamics at 0 temperature. And this has allowed us to observe that for a case of spin excitation, if the symmetry is not conserved by Hamiltonian, you have a strong oscillation of momentum distribution that correspond to strong oscillation of the symmetry. Thank you for your attention.
Thank you, Patrizia. Are there questions or comments?
Valentina.
Okay. Valentina upstairs, sorry, I mean, she.
Shout.
Okay, so you show that when you break the symmetry, you have this mixture between the most symmetric bosonic and the square, which is the most.
This is for the ground state of 2 plus 2 bosons, is an example, okay?
But you can get, in general, arbitrary mixtures between your young...
Yes. So it was just to say, now if you look to the eigenstate of my manifold, the symmetry is no more conserved. Okay, so this is just to point out this. Yes.
Okay, so it's not that that is selected by how you break the symmetry, no.
Okay. This is okay. The way in which we break the symmetry here is what particular. Now you are looking what happens if we break the symmetry in another situation. Here in this model, we were considered 2 Tonks gas interacting with a finite but large interaction, and this doesn't depend on because we are 2 Tonks gas. This doesn't depend on this value of G between the two, because in any case we put this and infinitive in a second time. Okay. But now we are Silvia is studying a situation in which we change the ratio between the 2 interaction strengths. Okay. So, but yes, this is indeed you are breaking very slowly, very little of the symmetry in this case.
Okay. Thanks.
Fabien?
Yeah, so very naive question. So at some point I expect this oscillation to die out and you go to some kind of diagonal ensemble. Can you predict like the average, from the initial side, the average
this is this is a very good question. To do this, we have not yet studied this. So, okay, here we have in a trap with a very small number of particles. So we don't see this, let's say, sort of thermalization that occur. So we need to increase the size of the system, because if not, it's a closed system with 4, 6. We did with 6 particles. It's not enough. Okay, but it's something that I want to do. Very nice. Because I'd like to know what is the symmetry at which the system.
Yes, please. Jacopo?
Indeed, but that dynamics is it's hard to solve, right? It's not analytical.
It's not?
It's not. I mean, you cannot solve it analytically. That oscillation.
No, but okay, you have.
It's an integrable spin change.
You have your okay for 6 particles. So you have a matrix Okay, for 4 particles, you have a matrix that is 6
sure.
times 6, and you have the eigenvalues, and the eigenstate you use Mathematica is
Okay.
there is no
so I guess the
approximation.
question- Okay, I guess the question is what happens if you increase in the thermodynamic limit? Does the oscillation remain, or?
Okay, I think, yes, I think that I'm pretty convinced that the oscillations are there. Okay, what will be difficult with a large system to say which symmetries are, because if I want to study what we did to really check what diagram was corresponding at a given time, or which superposition diagram, when you have a larger system, you have more tableau, so this is more difficult to check the state of this, and in one moment becomes impossible. So the idea here it was to start to understand the physics for a small number of particles in which you have everything under control. But yes, the oscillation will be there. What will happen is that at one moment you have a
The phase,
damping, then with a revival, but because it's a closed system.
So let's thank Patrizia again.